You're at the beach on a scorching 95-degree day holding an ice cream cone. But instead of racing against time to finish it before it becomes a sticky mess all over your hands, you can actually relax and enjoy it. This ice cream doesn't melt. It doesn't drip. It just sits there, perfectly intact, even under the blazing sun. Sounds impossible? Well, scientists in Japan have actually cracked the code. They've created ice cream that can withstand a hairdryer blast for minutes without turning into a puddle. Today, we're diving deep into the incredible science that's about to revolutionize your summer treats forever. Let's be honest, we've all been there. You buy that perfect ice cream cone, take 2 steps outside, and suddenly you're in a race against physics itself. The sun beats down, gravity pulls, and before you know it, you're wearing more ice cream than you're eating. It's one of summer's most universal frustrations, and for decades, we just accepted it as an inevitable fact of life. But then something extraordinary happened. Reports surfaced of Japanese manufacturer Kanazawa Ice creating ice pops and soft-serve ice cream that could withstand numerous heat-based assaults without melting. Videos went viral showing ice cream surviving conditions that would normally turn any frozen treat into liquid in seconds. We're talking about ice cream that could sit in direct sunlight and maintain its shape. The secret wasn't some artificial chemical concoction or space-age technology. The scientists behind this breakthrough had pumped their ice cream full of polyphenols, a class of antioxidant molecules found naturally in many fruits. The same compounds that give blueberries their health benefits and red wine its antioxidant properties were somehow creating ice cream with an almost supernatural resistance to melting. This wasn't just a cool party trick. This discovery represented a fundamental shift in how we understand frozen desserts and opened up possibilities that could transform the entire food industry, from manufacturing to distribution to our daily eating experiences. To understand why this breakthrough is so remarkable, we need to understand how regular ice cream works and why it's so eager to melt in the first place. Ice cream starts its life in massive industrial machines that churn a sweet mixture of cream and sugar in refrigerated drums. As the mixture freezes against the cold drum walls, mechanical scrapers constantly chip off the frozen film, preventing large ice crystals from forming. This constant agitation is what gives ice cream its smooth, creamy texture, instead of turning into a solid block of flavored ice. But here's where things get tricky. From the moment ice cream leaves that initial freezer, it's fighting a losing battle against temperature abuse. During transport from factory to store, from store freezer to your car, from your car to your home freezer, the ice cream repeatedly warms up slightly and refreezes. Each cycle creates larger, chunkier ice crystals. That's why sometimes your store-bought ice cream has that slightly jagged, icy texture. Now enter polyphenols, specifically tannic acid. When researchers examined ice cream treated with these natural compounds under a microscope, they discovered something fascinating. The tannic acid was linking up with water, fat, and protein molecules to create a rigid lattice network that held the water molecules in place, preventing them from accumulating and creating the drips you normally see on your cone. It's like giving your ice cream an internal scaffolding system. The scientist who really cracked this puzzle was Cameron Wicks, a food scientist who was studying at the University of Wisconsin when she first saw those viral videos of Japan's non-melting ice cream. Now working at General Mills, Wicks became obsessed with understanding exactly how polyphenols were achieving this seemingly impossible feat. The molecules were known for their health benefits, not their engineering properties, so she decided to dive deep into the mechanics. In her laboratory, Wicks began systematically experimenting with cream mixtures, adding different concentrations of tannic acid: 0.75%, 1.5%, and 3%. What she observed was remarkable. Almost immediately, the higher concentrations began to thicken dramatically. After chilling these mixtures for 24 hours, she discovered that the tannic acid had caused them to gel so strongly that the 3% mixture could literally be cut with a knife or turned completely upside down without falling out of a cup. When Wicks examined these samples under a microscope, she found the smoking gun. The higher concentrations showed more distinct fat globules, suggesting that the tannic acid was interacting with the proteins in the cream, creating what she described as a supportive network or barrier. This network prevented the fat globules from merging together, which explained why ice cream made with polyphenols resisted melting. The liberated fats from melted cream crystals simply couldn't flow and drip down. This discovery has massive implications that extend far beyond novelty ice cream tricks. Currently, commercial ice cream manufacturers rely on a cocktail of stabilizers to maintain texture and prevent melting. These include guar gum from guar beans, locust bean gum from carob tree seeds, carrageenan from seaweed, and xanthan gum from fermented bacteria. While the FDA considers these generally recognized as safe, there have been growing concerns about some of these additives. Carrageenan, in particular, has been linked to intestinal problems in some animal studies, and there haven't been extensive safety studies done on many of these gums. Some consumers report digestive discomfort, allergic reactions, and other issues after consuming products containing these stabilizers. Polyphenols offer a compelling alternative. These compounds, derived from common fruits and vegetables, have many documented health benefits with no known dangerous side effects. Researchers suggest that replacing current stabilizers with polyphenols from sources like blueberry powder could eliminate unfamiliar ingredients while actually supplementing the health benefits of sweet treats. The applications extend beyond health concerns. Polyphenols could improve ice cream shelf life by slowing ice crystal formation and enable manufacturers to develop more innovative, longer-lasting novelty shapes. This technology could also revolutionize food distribution to areas without reliable refrigeration, potentially bringing frozen treats to regions where they're currently impractical. Now, before you start imagining ice cream that defies the laws of physics, let's get real about what this technology actually delivers. As one researcher memorably put it, this isn't about freezing time or breaking the universe's physical laws. It's more like a bra for your ice cream, or a nice supportive pair of dessert hosiery. The polyphenols don't actually keep the ice cream cold, they just prevent it from flowing when it warms up. Over time, ice cream made this way acquires a pudding-like texture, although it continues to hold its general shape. Instead of melting into liquid, it becomes what researchers describe as a rubbery monolith, which isn't exactly what most people expect from their frozen dessert experience. Consumer expectations matter enormously in food science, and there's a psychological element to how we enjoy ice cream that includes watching it soften and melt. There's also the taste factor. Polyphenols can affect flavor due to their natural astringency, and researchers acknowledge that more work is needed to find the right concentration that provides benefits without compromising taste. Current research is focusing on optimizing both taste and texture, with particular interest in applying this technology to dairy-free ice creams, which typically melt faster due to their high water content. The future likely holds a middle ground, using polyphenols not to create completely non-melting ice cream, but to slow down melting enough to enhance the eating experience while maintaining the familiar texture and taste we love. So here's what I want to know from you. Would you actually want ice cream that doesn't melt? Are you team, give me the convenience of drip-free desserts, or team melting as part of the ice cream experience? And here's a bonus question. If you could design the perfect ice cream, what other impossible features would you want scientists to figure out? Drop your thoughts in the comments below. I read every single one. If you're fascinated by the incredible science hiding in everyday foods like I am, smash that subscribe button and ring the notification bell.